So here is our Frank-Starling relationship, and here is our determinants of fiber length, our end diastolic volume and pressure, our atrial pressure. As atrial pressure goes up, we increase filling, we increase all these things, and we increase the fiber length, and our force of contraction goes up. Okay? Now, here's what I want you to do. I want you to take everything I talked about in the last lecture and all the stuff relating to this curve that I've talked about so far, and I want you to forget about it. All right? Temporarily. It will come back because you have to know it for the quiz. But I want you to temporarily act as if I never said any of that. And we're going to do some playing around. And we're going to bring it back eventually, but for right now, I don't want to hear about it, okay? I'll let you know when it's okay to ask questions about it. All right? Good. So here's our system at steady state. Our cardiac output, that is the blood leaving the left ventricle, is exactly equal to the venous return. And we say that there is a mean circulation time of 1 minute. That means that on average, if I take like a red blood cell and I track it, on average it'll take 1 minute for it to go completely through the body and be returned to the right side of the heart. Okay? That's the mean circulation time. Okay? So blood's flowing fairly rapidly, 5 liters per minute. That's not trivial. So what is the total peripheral resistance? We just calculated it. We have a mean arterial pressure of 102, central venous pressure of 2. We have a cardiac output of 5 liters per minute, and we calculated 20 as the resistance. Now I want you to stop the heart. Stop it. Make up a reason. No ventricular output flow, right? The flow through the system does not instantaneously stop. It continues for a while, right? So eventually it's going to stop, but it takes a while for that to happen because you've still got a pressure gradient there, okay? You still got pressure higher in the arteries, lower in the veins. Blood is still flowing. And so you don't instantaneously just stop flow. What happens is your venous return gradually drops and eventually stops. And of course, your cardiac output stopped immediately, right? So again, here's our system at steady state. Here we stop the heart. Flow continues. Volume enters the venous compartment and volume leaves the arterial compartment because there's still a pressure gradient there and it flows, right? So what will happen to the arterial and venous pressure when that happens? What happens to the venous pressure when that happens? Goes up. My venous volume is going up, so my pressure goes up along with it, right? Because flow is basically blood's being transferred from the arteries to the veins because I've stopped the heart, but the pressure gradient is still there, okay? And we're still going to get flow. And the flow stops when the pressure gradient disappears, when the venous pressure rises and the arterial pressure falls until they're equal, okay? So that sounds like a fairly simple thing. You start at 100 on the right side. On the arterial side, you drop to about 50 and you're done, right? No, no, no. That is not true. The problem is that veins are more compliant than arteries, okay? And what that means is that the veins don't get as big a pressure increase for the change, for the same change in volume. Or another way of putting it is that the volume the volume does not goes up. It goes up a lot more for a given change in pressure. Okay, so for the same change in volume, the pressure will fall 19 times more in the arteries than it will in the veins. Then it will rise in the veins. The same volume might cause a 1 millimeter of mercury rise in pressure in the veins, whereas it's causing a 19 millimeter fall in pressure in the arteries. So if we want to calculate at what pressure we will stop flow, we have to do some algebra that I will not ask you to do. But for the record, there it is, and it's also in your notes. And if you do the calculation, you get 7 millimeters of mercury, okay? And this is called the mean circulatory pressure. So if somebody's heart stops and you look at the pressure in the veins, in the arteries, and it's less than that, it means they've lost blood, okay? So let's try to define what the relationship is here between our central venous pressure and our cardiac output. So there's our normal point. We started at 5 liters per minute, and we were at 2 millimeters of mercury of CVP. So there's our green dot. Now we stop the heart, and the cardiac output drops to 0. Flow continues. Volume leaves the arteries, and the pressure falls. Volume enters the veins. The pressure rises, and the mean circulatory pressure is attained. And we get 7 millimeters of mercury, and there is our green dot. 7 millimeters of mercury at 0 cardiac output. Now, here's the tricky part. What happens when I take my stop heart and I restart it at a cardiac output of 1 liter per minute? So now we have volume being pumped out of the venous compartment and pumped into the arterial compartment, because flow doesn't just instantaneously go across the system and attain 1 liter per minute. It takes time for that to happen, and you have to build a pressure gradient across the system. And when the pressure gradient is adequate, then you'll have a flow of 1 liter per minute across the system, and you'll be at steady state. But in order to build that pressure gradient, you have to remove volume from the venous side, and you have to add volume to the arterial side. And you will do that until the flow is equal, cardiac output of 1, flow across the system 1. Okay? So we can do a little bit of calculation to decide what that pressure difference has to be. The resistance of the system, we calculated already, 20. Okay? Told you it wasn't just an academic exercise. We're going to use it. So the TPR is 20, that's our R. Our flow is 1. So we need a delta P of 20 millimeters of mercury. Okay? Well, I know that if I take enough volume out of the veins to make it drop 1 millimeter of mercury, I'm going to increase the pressure on the arteries 19, because my veins are 19 times more compliant than my arteries. How convenient. Okay? So I get a 1 millimeter drop on the venous side. That will give me a delta P of 20. Okay? Because I get a 19 millimeter rise on the arterial side. Their arteries less compliant. All right? So, and there's our next point. Cardiac output 1, central venous pressure, a 1 millimeter drop, and we have 6. And you can keep doing that if you want, and you can calculate each cardiac output, and you will see that it is a linear relationship, okay, between central venous pressure and cardiac output. So, do recognize, and I have highlighted it here, the vascular function curve is only a part of the control in terms of the cardiovascular system. And the reason I say that, and it's the same thing really with pretty much everything that we're going to talk about, that we talk about, the only way to understand the cardiovascular system is break it up into its individual parts and talk about each part individually, okay? Because it's really, really complicated. So all we can do are talk about the factors that influence it. This is one factor that influences. My cardiac influences it. My cardiac output drops, my central venous pressure rises, okay? And this has consequences. It is not academic, okay? I'll get to it. So here, I'll get to it now. Here's our heart failure patient. What's happening with her venous pressure? Cardiac output's down, so the venous pressure is high. Anybody remember what her jugular looked like? It was distended, which is a classic sign of somebody who's in congestive heart failure, okay? Jugular venous distension, all right? You can actually see it. Sometimes you can see it pulsating, okay? So that is one way we generate the sign. Now, if we have hemorrhage and I lose blood, let's stop the heart. What's the mean circulatory pressure, higher or lower if I remove blood from the system, if I remove a liter of blood or something? Lower, right? So now at a 0 cardiac output, I'm at a lower central venous pressure. Now, what happens if I increase cardiac output to 1 liter per minute? Well, my resistance is 20, and my cardiac output is 1, and I need a delta P of 20 millimeters of mercury. If I remove enough volume from the veins to drop it 1 millimeter of mercury, I get a 19 millimeter rise on the arterial side, and I get a delta P of 20. So I put another dot there. And as you might guess, based upon those 2 dots, we have a parallel shift in the line. Okay? And you get a shift downward. And if I give blood, then I get a shift upward, like that. Okay? Increased blood volume, shift upward. Decreased blood volume, shift downward. Okay? So there's our central venous pressure cardiac output relationship. Vasoconstriction. What does that look like? Well, my total peripheral resistance goes from 20 to 40, so I doubled it. Stop the heart. What happens to the mean circulatory pressure? And we are going to assume that when we increase total peripheral resistance, we're talking about constriction at the arterioles. Okay? So figure it's right there in the arterioles and nowhere else. What happens to mean circulatory pressure? Anything? No one wants to stick their neck out?
Increase.
I hear an increase. Anybody want to disagree with that? Okay. As it turns out, the arterioles are only a very small part of the total vascular compartment. And when you constrict just the arterioles, you don't really change a whole lot elsewhere. So in fact, you don't have a significant change in the mean circulatory system. But thank you for guessing. And it's not a bad guess in that if I constricted like all the arteries everywhere, and if I constricted the veins too, then the mean circulatory pressure would increase. But now we're just talking about the arterioles, the principal points of resistance in the body, okay? So if I increase cardiac output to 1 liter per minute, my cardiac output, Q1, total peripheral resistance is now 40. Now I need a delta P of 40, not 20, to drive a flow of 1 liter per minute across the system. So 1 millimeter fall in CVP gives me a 19 millimeter rise on the arterial side. That gives me 20 millimeters of mercury difference. And now I'll take another millimeter of mercury away and make it a 2 millimeter fall. And now my arterial will rise 38 millimeters of mercury. And now I'll have a delta P of 40. So instead of a drop of 1 millimeter of mercury on the venous side, we have a drop of 2 for an increment in 1 liter per minute cardiac output. We have a change in slope in that relationship. Okay? And this is what the relationship looks like when you change the resistance. Okay? Total peripheral resistance.